We're going to now look at using the derivative to find where a function is increasing, where it's decreasing, to be able to find your local extrema, local max, local min, and absolute max and absolute min if they occur. I think this is kind of exciting. We're now getting into the fact that in our careers before with mathematics and algebra, we weren't able to graph all types of functions. And now we're using calculus to help us be able to graph functions. So first thing, and we've already kind of looked at this before in the past, remember the derivative is telling us about the slope, the rate of change of our function f. And so we want to suppose that f is continuous on a closed interval ab, and it's differentiable on that open interval ab. We know that if our derivative is greater than 0, at each x value contained in our open interval ab, that our function has to be increasing on this interval ab. We saw that if we found that our derivative was less than 0, and if this occurs at each value of x in our open interval ab, then f is decreasing on this closed interval ab. Okay, so we've already talked about that. We talked about if we find that f prime of x is equal to 0, that things could be leveling out. We could have something that looks like this, right? We took the derivative here, we would find that that slope was equal to 0. We found that if we had a maximum value and we took the derivative at that maximum value, that slope of that tangent line there was also equal to 0. Same thing with a minimum. And so we're going to use this fact to help us find max mins and to help us graph these functions. So the first derivative test, basically to use this first derivative test and to find our local extrema, local max and local mins, we want to do the following. So we want to suppose that C is a critical point of a continuous function. So remember, we were looking at critical points at the beginning of this chapter, and critical points occur when our derivative f prime of x is equal to 0 and where that derivative is undefined. If it's in the domain of the original. Okay. So f prime of c is undefined, but f of c is defined. If it's not defined, then we have an open circle there and our function isn't continuous. And we were saying that this is a continuous function. Okay. So let's go back and start breaking this down again. So suppose that C is a critical point on a continuous function and that f is differentiable at every point in some interval containing C. But this is important, except possibly at C itself. We'll talk about that in a second. So remember, when we're looking at the graphs, we're always moving from the left to the right. So moving along the interval from left to right. Okay, so if we look at our derivative and our derivative is going from negative to positive. So think about this. Our derivative is going from negative, so it's a decreasing function, and then it's going to be going upwards, left to right, because the derivative is positive. This is my value here at C. So if that's the case, notice that you get a local minimum at C. So if we go from the opposite direction, if our derivative was positive, we know our function is increasing from left to right. To negative, So at C, it's changing direction, and now it's going to be decreasing. Then we have a local maximum at C. If we find that it doesn't change signs, that derivative doesn't change sign, then what's happening is f prime does not change signs at C. That is, f prime is positive on both sides of C or negative on both sides, then f has no local extrema. So this would be the case up here where it leveled out, but then continued in the same direction. So it could be decreasing, level out, and then continue in the same direction. So if that's the case, then there's no local extrema that exists at C. Okay, so here's a couple of different situations of what could be happening on a graph. And if we wanted to find where we had extrema, local max, local min points. So recall, if we're on a closed interval, so this is in using the example that we're on a closed interval. Let me just move things around for a sec. So recall if we had things at a closed interval, then an absolute max or an absolute min or a local max or a local min can occur. And so this graph that we're looking at is on a closed interval. And so notice that this value when x is a, that's the lowest y value that we're hitting on the graph. And so that's where this would be a absolute min. Notice that if we're following the graph from left to right, at first we're going upwards. And so we're going increasing function. And so if we're increasing, recall that our graph is, if our derivative is greater than 0. If our function is increasing, our derivative is greater than 0. So here, if it asks us where our function is increasing, what intervals, we remember intervals we use are our x values. So it's starting at A, and notice that it's leveling out at C sub 1. So going to C sub 1. Then notice that at C sub 1, we're also increasing until we hit C sub 2. So we would put this union. C sub 1 gave us a slope of 0, so we're not including it, to C sub 2. If I look at this again, left to right, I can see that it's going upwards from C sub 3 till we hit C sub 4. So union C sub 3 comma C sub 4. And then I don't see it increasing in any other place. So looking at where our derivative is less than 0, this is where, again, our graph is decreasing. And they're going to ask you to look at graphs and find where it's increasing and decreasing. So looking at where it's going down left to right, notice that it's going down from C sub 2, starting at, to C sub 3. Union, and then it's down from C sub 4 to C sub 5. And then again, decreasing from C sub 5 to B. So again, interval notation, always use the x values unless when there's one time we're looking at range. That's the only time we use y values when we're looking at interval notation. Notice that there's places where the derivative was equal to 0. And so horizontal tangent line. But this was no mess, didn't have an extreme. And then look at this piece here, our derivative equal to 0. This is a maximum value. Here, our derivative, Here, though, we have a sharp corner. So this is where our derivative doesn't exist, but notice that it is existing for our original function. So when we took the derivative, we would look at where is it undefined to find those values where it doesn't exist. Again, we find that the so this is not the absolute min. Where it's increasing, decreasing. We're going to look at finding the derivative, setting it equal to 0, and finding those critical numbers. And those critical numbers, we'll test each side, plug it into the derivative to see if it's positive or a negative function. And then if it changes direction, we know that local max min, possibly an absolute max, absolute min occurs. Okay, so here's another example. So from here, you should be able to look at this graph. You should be able to find the intervals where it's increasing, decreasing. Assume that these are not going on, that these are closed points here. And so if we look at this, notice that, let's just start with increasing. So we're going up, and these are in intervals of 5. So this is negative 20. We hit negative 15. Union. So again, we're going up. So this is my x values, negative 15 to negative 5. And then I start to go up again. So my value here, that looks like about 2.5. So let's say in 2.5 to this x value of 10. And then I'm going up if I look at x equals 10 to x equals 20. So union 10. Oops. Okay, so same idea for decreasing. We're going down, we're looking at from negative 5 to 2.5. And the graph can go down any other place. And then it wants us to identify absolute okay. So I don't know how long you guys were gone for. So let me just pause this real quick. So if we want to look for the absolute max, and that's what an absolute min, that's what I would look at first. Is there the smallest y value on here? The thing is that this is an open circle. It looks like, almost negative 10, but this is an open circle here. So there's nothing that's getting us to negative 10 itself, but we're always getting closer and closer to that y value of negative 10. So there's no absolute min. For max though, notice that when x is 20, this is like a closed circle here. And so we have an absolute max. That's the highest y value we hit is 15. So the absolute max is 15 at x equals 20. And then looking for local max, local mins. This is a close point here. So this is a local min. That y value is -5. Of -5 when x is -20. Let's just do local mins right now. And so right here, this is where the derivative doesn't exist. It's a sharp corner, but there is, it's defined there. We have a local min of -5 when x is 2.5. That looks like that's the only other local min. Local max. And that y value is 10. So a local max of 10 at x equals 0. This is closed here. So we have a local max when x is at 5 when x is 10. And we already got this as our absolute max. So looking at the graph, you should be able to find where your function's increasing, where it's decreasing. You should be able to locate absolute max and absolute mins. So now let's jump into looking at, given a function, being able to find where it's increasing, decreasing.
Sorry,
And
I got a question. Sorry for disturbing. You've written local max at 5 when x equal to 10. I think.
Yeah. The local max here, that y value is 5, but the x value is 10 here.
Okay, got it. Thank you.
Yeah. Any other questions?